Hi students, it's Ms. Vernon and I'm here today to teach on lesson 1.2, day 1. We will be spending 3 days on lesson 1.2 and we'll be learning a lot of vocabulary. So it's very important that you take good notes as this vocabulary will be the foundation as we move forward throughout pre-calc. So some of the vocabulary that we are going to be focusing on today are domain and range, function and relation, and continuity. Some of these are words you definitely have seen before, while others are going to be new and we'll have to define them and spend a little more time working with them. Let's go ahead and get started with the first chunk of vocabulary. The first chunk of vocabulary we'll be looking at is what we call function and relation. These two pieces of vocabulary go hand in hand. A function, many of you will probably recall, is the situation where each input has exactly one output. We may have said this in the past as each x value has only one y partner or one y coordinate that is associated with it. Do you remember the test we used to test this out if we're given a graph? Hopefully you said it was the vertical line test. That would have been correct. The vertical line test is the one where we drag a vertical line across a graph and we want to make sure that it only touches in one point at a time. The second word here is relation, and a relation is just a relationship between two variables. It doesn't have any rules or extra qualifications for it. Basically, there are infinitely many relations, but some of the relations get the extra special title of being a function because each x only pairs with one y value. Here's a picture to represent this. In this picture, you'll see that each x is mapping, they use these arrows to signify mapping, to a y coordinate. Now, notice that x4 is mapping to y3 and x3 is mapping to y3. This is totally acceptable and is still defined as being a function. So I could have all my x values going to the same y coordinate, and that's okay. The situation where it becomes not okay is if I have an x value that pairs up with two different y values. In this case, this x coordinate has two y partners, and that is what makes it not a function. Okay. Now, as we said before, we have this thing called a vertical line test. And how the vertical line test works is if I'm given a graph, I'm just going to draw some arbitrary graph, and I were to drag my vertical line across this graph, if it touched the graph in more than one spot, so in this case, it's touching my Z shape in 1, 2, 3 spots, that would mean that the purple graph is not a function. Now, if it only touches the graph in one spot, it would be a function. For example, if I draw a U-shaped graph and drag this blue line across that, notice that it only touches the U in one spot at a time. Therefore, I would state that this blue or this U-shaped graph is a function as the vertical line passed it. Okay. Again, that was probably a review. So let's get into some of the information that isn't as common right after we do one more example reinforcing it. So here are two graphs and an equation. I'm going to number these 1, 2, and 3. And I want you to determine which of these are a function and which of these are not a function. All right, you should have said the first one was a function. It would pass the vertical line test. You probably also said number 3 was a function very quickly. Again, it would pass the vertical line test. The middle one, or the equation, is not a function. And let me explain why. Because the y term is squared, I would need to isolate that in order to graph it. And in order to isolate it, I would have to take the square root of both sides. When I do that, I am left with y equals plus or minus the square root of 3x plus 5. If I were to go and graph this, I would end up with this kind of sideways U-shaped graph, or this U-shaped graph that's turned on its side. And in this case, that would not pass a vertical line test. Typically, if I'm given an equation, I'll graph it and see if it is or is not a function based on the vertical line test. However, if the y value is squared, it's typically not going to become a function, because in getting y by itself, it will force us to have two parts. All right, let's move on to the next set of notes on domain and range. You probably remember learning about domain and range last year in Algebra 2. The domain of a function is the possible input values. We oftentimes refer to input values as the x values because most of the equations we work with are y equals an x term of some sort. In pre-calc, we'll be requiring you to calculate these algebraically. This is very important. You don't want to forget about how to calculate them algebraically. So I'm making a special note to say, hey, this is important. And I'll explain that in just a second. The range of a function is the possible output values. So basically, if you look at the graph, what y values show up on the graph? Now, we'll find this graphically still. There is a way to find it algebraically. We're just not ready to do that quite yet. So let's jump in and talk about, okay, so I can find the domain from a graph, Miss Vernon, but I don't know how to find it algebraically. Well, let's take a look. Domains of a graph are broken down or failing or not working if they break mathematical reasonings that we have. So there are two situations in which the domain will be interrupted, or the domain being everything working will not end up working. The first is if we divide by 0. So the only time this one is going to come into play is if you are going to be given a fraction. So if you have a fraction, you will want to take a look at this one. And basically how we do this is we say, if a value causes the denominator of the fraction to equal 0, it is considered to be undefined. And so mathematically, how we calculate it is we say the denominator cannot equal 0. And if it does, we'll exclude those values from our domain. So then we're going to, again, exclude these values. Because if the denominator equals 0, we broke the rule of math of dividing by 0. The second situation that we encounter with this is if we take the square root of a negative number. As you know, the square root of a negative number is an imaginary number, and we can't see that on a graph, so it doesn't exist. To algebraically show this, we would want to make sure that the terms under the radical are greater than or equal to 0. You can take the square root of 0. It equals 0. The reason we want to make sure this happens is because, again, you can't take the square root of a negative number. All right, let's go ahead and revisit a problem from earlier. In this problem, I'm asking you to find the domain and range. Now, I've provided us with a graph here to help us out specifically for the range portion, but also to explain the other part. So as I look at this, the first thing I note is that the domain is going to be broken up because I have a denominator. So if I want to algebraically show this, I'm going to want to say x squared minus 16 cannot equal 0. Now, because there's no middle term, I am able to solve this algebraically by adding 16 and taking the square root. However, I also recognize that this is a difference of 2 squares, so I'm actually going to choose to factor it. This will factor to x plus 4 times x minus 4. And when solving this algebraically, I can go ahead and set each of these parenthesis terms not equal to 0. This is essentially using the zero product property that we learned at the beginning of the year. This tells me that x cannot equal 4 and x cannot equal negative 4. I'll be excluding these from the domain. As I look back at my problem, I don't see a square root symbol, so the second issue that comes up with domain is not going to be a factor that I have to worry about. All right, I'm going to come over here and I'm going to state my domain. I'm going to use the letter D for domain. And I know that this function is existing everywhere except not at negative 4 and not at positive 4. So I'm going to write my domain in interval notation, negative infinity to negative 4. It also exists from negative 4 to 4, and then again from 4 to infinity. Now, we haven't seen it where we've had 3 chunks of interval notation before, but we use the same type of notation we learned with inequalities earlier this year, using that union symbol to indicate the 3 areas where the graph exists. Next, I want to take a look at the range of this function. Now, as I look at this function, I am going to look graphically, and I sometimes find it's easier to see if I drag a line. Now, this is not the vertical line test. This is just me giving you a visual cue. So as I drag this line over my graph, is there any point where the blue graph does not exist? And as I go, it appears the blue graph is always existing. So when I state my range here, I'm going to state my range as being negative infinity to infinity. All my y values are going to show up on my graph. So therefore, my range is negative infinity to infinity. Domain and range tend to be a tricky one for students. So I have another one for us to take a look at. Find the domain and range of the following problem. Write your answer in interval notation. So I know eventually I want to state my domain and I want to state my range. As I look at my function that was given, it's not a fraction, so I won't have division by 0. However, it does have that radical, so I'm going to need to evaluate that a little bit farther. If you recall, we said mathematically we cannot take the square root of a negative number. So we want to make sure that x plus 3 is greater than or equal to 0. Therefore, x has to be greater than or equal to negative 3. Now, if I think about this with interval notation, I would have negative 3 to infinity. I know that I need to look at the graph to determine the range. However, some of us might be able to make this connection without. Recall that a square root function kind of looks like a hill shape. It grows very gradually. Notice that this is where it's starting. That is at negative 3. So it makes sense that my graph, my y or my x values, went from negative 3 to infinity. If I think about where my graph is starting, as I evaluate or look at the range, I see that it starts at 0, and that point actually exists. So my range for this one will go from 0 to infinity. Again, for right now, we're going to graph these to identify the range. All right, the last set of vocabulary for today is what we're calling continuity. Continuity is a term that students sometimes get confused with. Let's go ahead and take a look at some graphs and some different scenarios. There will be 4 scenarios we will evaluate or learn about here related to continuity. The first scenario that we have is a continuous function. So if a graph is considered to be continuous, you'll notice that as I trace this graph, there are no gaps, holes, or asymptotes. Therefore, we say it is a continuous function for all x values, or all points are defined. Simply stating, I can trace that graph without ever picking up my finger. All right, the second type of continuity that we can end up having is what we call a removable discontinuity. A removable discontinuity is a scenario where we have one single spot that does not fill in. So there is a point in the graph where it is not defined. It is called a hole. Now, if you remember way back to Algebra 2, you may have learned that a hole can exist if you have the same factor on the top and the bottom. So you might have some other stuff happening as well. I'm just making up some terms here. But because I have this x minus a factor on the top and bottom, that becomes a hole. So that is when a hole occurs. Now, algebraically, that's what we look for. But if we're looking at the graph and there's this little circle opening, we say it's a removable discontinuity. I could fill it in if I knew that one value. All right, the next 2 types of discontinuities or continuity vocabulary that we have, we give it a bigger name and we call it a non-removable discontinuity. So non-removable one can be one of 2 scenarios. The first is called a jump discontinuity. In this scenario, the graph continues, except for as it goes, you'll see that there will be a gap where you'll have to physically pick up your pen before you can continue to graph it. Okay? It says it has a different value depending on the side at which you approach it from. So there's a jump here, and as I come from it from this side, it would be this value. But as I approach that same x value from the other side, it has a different value. And that's what that means. It's just talking about limit a little bit. And we'll revisit the limit conversation as we move forward in this section. The final vocab word that I have for you is an infinite discontinuity. Now, again, I want to stress, non-removable discontinuities could be jump or infinite. Again, with an infinite discontinuity, you'll notice that you have to physically pick up your pen and relocate it. And that is why it's considered an infinite discontinuity. Now, this infinite discontinuity occurs when you have a vertical asymptote. We'll formally define this later, but a vertical asymptote occurs when the denominator is equal to 0. That is when a vertical asymptote occurs. But again, that's going to show up in the vocabulary as we break down this section 1.2. For right now, I just want you to be able to recognize the 4 different types of continuity or discontinuity that we can have. So I'm going to zoom out just so that we can get them all on the page. So in green, we have continuous. Notice I never have to pick up my pen as I trace that function. In yellow, it would be a hole, a single spot on the graph that is missing, but everything else would work. Then we have 2 different scenarios where they're called non-removable. The first is a jump discontinuity, and the second is an infinite discontinuity. Okay, that's the lesson for today. Be sure to pause the video or go back and rewind it if you needed to get some of these terms down a little bit more. And be sure to take care of doing your math online, your Math Excel work, as it's going to help reinforce this vocabulary. Have a great day. We'll talk to you soon.